Welcome to lesson 18. Okay, here's where things get a little bit sort of complicated, but not really, just a lot. When you're looking at groups of carbonyls, there's a way that they react and a way that you can transfix one to another. So we can use this synthetically, and if you want to consider this, it's almost like the stability of all of these goes towards this guy. So this is not necessarily the most stable, but kind of is. Let's put it this way. This guy is much more reactive than this one. There's an easy reason for that. Because each of these guys are going to leave in the process of something else replacing them. And a Cl- is more stable on its own than an NH2- is. That makes sense, right? Because a Cl- is kind of like an adult leaving home. He can take the negative charge. A Br- would be great at doing that too, right? These are very good leaving groups. But you take an NH2 and make him exist on his own, and that's kind of like kicking out a 3-year-old. It just doesn't work very well. It'd be much better for you as an adult to leave home. At least I would hope. Okay, so we use this in terms of our reactivity instability. And if you just sort of think about what your R groups are, and you think about what it is that your leaving groups look like, that's pretty easy to see. Because this is more stable than that is. This is more stable than that is, because now we have no resonance anymore, right? These two are about the same, depending, and that's more stable than an NH2- is, due to electronegativity, right? So, let's use that as a general rule when we're proceeding, okay? And if you recall last time, we talked about what the general mechanism was for a nucleophilic addition and elimination of a carbonyl with a charged, well, any type of nucleophile really. If we look at it with when the nucleophile is charged, this OH- comes and attacks this carbonyl right here. Why does it do that? Again, recall that oxygen is partially negative, leaving that carbon partially positive. Negative goes to positive. It's really that simple. Electrons move up. Now at this point in time, we've got a carbon with 4 bonds. A carbon bound to 2 oxygens is, generally speaking, not very stable, especially if one of those oxygens has a negative charge to it. So these electrons actually start coming down. And one of these two things then have to decide who's going to be better at leaving. So this guy in this particular case is going to be my example of something general that's just leaving. And that's going to give you a COOH. And that COOH, basically, this OH just replaced whatever that B was, right? Hey, it's not so bad, right? If you have a neutral, sorry, I just realized you can't see everything. If you have a neutral nucleophile, the same type of thing really works. This nucleophile would attack there and come up, but then some form of base within the reaction mixture, it doesn't even have to be something that you're adding, sometimes it's just a solvent, whatever that may be, or sometimes it is something that you're adding, would then need to come and remove that hydrogen so that you get to a neutral place. And yes, this is an equilibrium though. Okay, so you need to make sure that you have enough base to remove that hydrogen to even make it go this way. And then the same type of step will occur. So the reaction will occur if whatever B- is, or B with 2 electrons are, and in this case it would be negative as well, if it's a better leaving group than the nucleophile. So if you look up here at the chart, if your stability is in accordance with that rule, then you're fine. If you are trying to kick out an NH2 with a Cl-, that's not going to work. But you can certainly kick out a Cl minus with an NH2. That's not a problem. So that's what we mean by that chart. Okay. So now we've got to talk about each one of these reactions and how they really react. Let's begin with esters. Esters can undergo a reaction with NH3 to give you this type of product. We know that already from the last page, right? Because here's our ester. It's more reactive than our NH2 because OH minus or OR minus is a more stable leaving group than an NH2 minus is. This is especially helped if you have a little bit of heat. You can also use NR3 groups. That's not a problem. So that's going to go by the same type of mechanisms that we just went over. However, you can actually even switch out what this R group is. I'll show you that in a minute. And you get an R prime there. Or you can go and make this carboxylic acid. In this case, we need some acid help for us. So essentially, that means that you can change out that R group for this hydrogen or that R group. You do that by having excess of either of these in the reaction mixture, by the way. Okay, so let's look first at the acid catalyzed ester hydrolysis equilibrium. This isn't a full equilibrium reaction, so be aware of that. Everything here is in equilibrium. So first things first, oxygen comes and grabs a hydrogen. Electrons go back to whatever conjugate base you would then make. Water takes its electrons and donates it to the carbonyl, allowing this carbonyl's electrons to go up. You make this first tetrahedral intermediate. A base will come and remove that hydrogen, doing what I refer to as cleaning up the reaction simply by taking off the hydrogen and making everything neutral. Now again, you have a tetrahedral intermediate, but carbon bound to three things it really isn't stable when it's three oxygens. It's just not. It's pretty reactive. So these electrons then say, hey, I just found another acid to hang out with. Electrons go back to the base. You then have a situation where we now have a really good leaving group that we just made. Because now when these electrons come down and that goes out, you just made an alcohol. And an alcohol is just as stable on its own as water would be. Then the conjugate base from this guy over here comes and removes that hydrogen. Electrons go back to the oxygen, and bam, there you go right there. Now, you actually use Le Chatelier's principle in order to push this reaction to happen. Otherwise, it has nothing driving it. So remember Le Chatelier's principle. It said that if you increase the concentration of one thing on one side, it's going to shift to the other side, right? Well, that means that we need a large amount of this guy. If you have a large amount of this guy, then he'll push this to happen. Oh, but we probably need a large amount of water too. And that's exactly what the reaction mixture looks like. You have a large amount of acid and water, and it pushes things to this point. If you're getting out a low boiling alcohol, or one that's a lower boiling alcohol than what these guys are, then you could actually even distill out this alcohol. Le Chatelier's principle also says is as you remove a product from one side, then that means it'll shift towards that side, right? So we're removing this, it'll continue to shift this way. That's another way to sort of push this reaction to happen. Now that's all good and true, but there's always an exception. The mechanism really changes when you have a tertiary alkyl group present right there. And this is a lot easier reaction mechanism. It's just not something that you would expect to have two mechanisms. So we sort of start the same way though. This carbonyl, the oxygen comes and grabs the hydrogen, electrons go back to whatever conjugate base you just formed there. And then like this magic swoosh happens, okay? Electrons from this tertiary group here shift over there. And these electrons shift up. This is similar to what you would have, at least in theory, to like a methyl shift. The electrons are just shifting over. You get your carboxylic acid product that easily. It's really quick that you make this guy. But you leave a carbocation on a tertiary alkyl group. Then this sort of gets cleaned up. Water comes in and attacks. Conjugate base from way over here comes and removes the hydrogen right here. Electrons go back, and there's your other alcohol that you're going to get as a side product. These again are in equilibrium though, so you still need to drive them the way that we would up here, up above. Okay. The same way that you can catalyze this reaction with large amounts of acid, you could also do it with a base. We show you both because, as you've seen in the lab, sometimes you can't use a strong acid or a strong base. It could remove a protection group. It could alter some other part of the molecule. So it's really good to at least know an acid and base form of a reaction, simply because that's the way that you can make sure that it will work. So here we have a strong base. Negative charge goes to partially positive charge. Electrons go up, and as they come down, they go back around. Doesn't this look exactly like what we just did at the beginning? Yeah, because it totally is, right? Now, you got to be careful, because when you have a lot of base, it'll remove that hydrogen from your carboxylic acid, right? So once you have that carboxylate, then at the end of your reaction, you have to neutralize everything as part of your workup. Be aware that this is another thing that can happen. If you have a large amount of water, then you could end up making sort of this other intermediate. You want to have large amounts of excess base to avoid that from happening. Now, the cool thing of it is about the base catalyzed is this step right here is not reversible. It's not. So once you get to this stage, boom, it will actually react. You actually get final product there, and it's not going to go back and unreact on you, if that's a word. Okay, thank you very much.